Yes, this is what a chemical vapor deposition. You can observe in the first figure. This is how the schematic diagram of a chemical vapor deposition. The difference between PVD and CVD is in the PVD, physically we are going to deposit a filament on the substrate or the workpiece. But here in CVD, there is a chemical process, okay, and because of the chemical process, it generates the byproducts, and those byproducts are deposited on the substrate or workpiece. That is called a chemical vapor deposition. You can observe here, and this is what the a chamber, okay, and these are the one reactant and another reactant, and in the chamber these two will react and produces the byproduct, and that byproduct is deposited on the either tools or stainless steel and these substrates. Okay. Yes, chemical vapor deposition, it is a chemical reaction. It is a chemical reaction between the a mixture of gases. So it is the chemical reaction between a mixture of gases and the heated substrate. Okay. So on the heated substrate, and these chemical reactions will take place, and the byproduct is deposited, or the solid film is deposited on the substrate. And this chemical vapor deposition or CVD is a process where one or more volatile procurants, that is what the gases or reactants, are transported via through the vapor phase. Yes, here also there is an vapors. There is no liquid or solid. Here only a gaseous or vapors are deposited, and this entire thing is takes place in the reaction chamber, that is with the, it may be with the help of vacuum or without help of vacuum. Okay. And this is what we call it as a chemical vapor deposition. So chemical vapor deposition means it is a process in which the chemical reaction taking place between the two gases or reactants, and because of that it will produces the byproducts, and those byproducts are deposited on the substrate, and entire process is taking place in the reaction chamber. This is what we call CVD or chemical vapor deposition. But PVD means, what happens in the PVD? Here in the vacuum, okay, in the vacuum chamber or in the pressurized vacuum chamber, there is a target, and the target is going to heat, and because of the heat, the target will produce the vapor, and those vapors are deposited on the substrate or workpiece. That is what the physical vapor deposition by heating. But here we are not doing any physical, just because of the chemical reaction between the gases, it produces the vapors, and those vapors are going to collect on the substrate. Yes, you can observe here. These are the two reactant suppliers, okay, gases, and these are the valves which controls the flow rate, okay, and they will in the, this is what the a chamber, a reaction chamber, okay, and this is a substrate, and this is a substrate holder, or a just a table, on that we are going to place the substrate or workpiece, okay, and deposition chamber or reaction chamber. Here there is a reaction takes place in this, okay, and because of the reaction it produces the byproducts, and some of the byproducts vapors are deposited, and remaining byproducts are going to the outside. It may be used for the recycling purpose or just to the atmosphere. Clear? So this is what the schematic representation of CV. So many materials may be deposited using this CVD and related techniques. Either we can use the metals, oxides, nitrites, okay, sulfides, phosphides. Okay, so these are the different materials we are used to coat on the substrate. Okay, and example preparation of this tin based boron oxide, tin based boron oxide. TiB2 means tin based boron oxide. Melting point, it is, you can observe that melting point is 3325, which is very high temperature when compared to the PVD. So PVD, what happens? The temperature is, what happens in the PVD? The temperature is maximum of, so maximum of 500. Okay, so but here the temperature is 3325, so which can use for very high temperature. In the graph in the previous class, uh, uh, we discussed about one graph. Okay, so temperature versus coating film thickness. So in the temperature, high temperature, there is a chemical vapor deposition which can operate more than 100 or 2000 degree centigrade. So see here in the one example, in this example the melting temperature is 3025. Okay, and deposited by the CVD at an 100, sorry, 1000 degree centigrade. And this is what the chemical reaction taking place. And with the first CVD, it's a hard coating. Of course, it is a hard coating, and it is generally used for the cutting tools. For the cutting tools, we are using this type of coating process. And here also used for the some of the structural glasses also we can use this type, and that is for the solar cells, catalysts, membranes. For these purpose, we are using this glass. Okay, but in the metal, if you use this process, it is for purely for the cutting tools. And this is a chemical reaction taking place inside the reaction chamber and produces the byproducts, and this product is deposited on the substrate of metal. Okay, a metal at the surface mele this byproduct going to deposit. It is in the vapor form. And see, this is what the steps in the CVD process. Just like a PVD, here also some steps are there. First, gaseous reactant, we have to supply the gaseous reactant. Next, absorbed intermediates and gaseous byproduct and solid product. First, we have to supply the gaseous reactant to the combustion chamber, sorry, a reaction chamber. In that, there is a reaction taking place and produces the byproducts, that is in the form of gas, again vapors. Okay, and last step is it is deposited on the solid product. It is become a solid. And after this process, you have to cool the entire process because it is operating in the high temperature. So here temperature is very high, and also we need a more cooling system when compared to the PVD. So PVD, it is operating in the less temperature, so it need a less cooling system, but here it is operating in a high temperature, so it need a very high cooling system or ventilating system. Okay, so energy consumption is more in case of chemical vapor deposition when compared to the PVD. So in PVD, the heat temperature or energy absorption is less, but here energy absorption is more. Clear? Some of the examples, just like the PVD, there are evaporative and sputtering process. But here, just like a PVD, here also same thing, plasma assisted CVD. It's a one process, plasma assisted PVD. Here same thing, the process is same. Okay, the entire process is same. There is an gases. Okay, and it takes place the reactions. Here it produces the reactions and byproduct, and that byproduct is going to deposit step by step, going to deposit on the substrate. So like this, the atoms are deposited on the substrate. There also same thing, substrate, on the substrate diamond film, it's a one different type of process. Okay, so it is depositing on the substrate. And here it is a chemicals, two chemicals and chemical reaction, and at a temperature of 2000 centigrade. And future directions in PVD and CVD. So these PVD and CVDs are after, of course, these two are the advanced process when compared to the conventional one. Conventional one, it's earlier in 90s, in 60s and 70s, they are using. So which are the conventional process? Which are the conventional process? Yes, it's a spray painting, quenching, okay, or dipping. So these are the conventional process. and CVD and PVD are the advanced one. And next in the future, and these techniques may use for the nano composite coating. So this is for the advancement. So nano composite coatings these can use, okay, for the smart material production. So nano means 10 to -9. The thickness is very small, okay. So for that process we can use these techniques, okay. These are the some future techniques. And after this CVD and PVD, so some other advanced technique like ion implementation. So ion implementation, it is an another process. We already discussed in the earlier class this CVD, PVD, ion implementation. So these are the advanced process. So ion implementation means it is an embedding the atoms. So embedment means embedding the atoms on the workpiece or on the substrate. So if it is a substrate and on the surface of the substrate the atoms are embedded. Okay, it is called ion implementation. First we have to produce the ion. Okay, either by with the help of energy or electricity. Okay, or chemical reaction, and that atoms or ions will start transmitting onto the substrate of workpiece. So this is what we call it as a ion implementation. So embedding the atoms on one or more foreign element into the substrate surface with an high energy beam ionized particles. See, we just observe. So this is a implanted ions. So here this is a target. Okay. So this target either it is by providing the energy or providing the electric uh, city or by providing the heat. This produces the atom, free atoms, and these atoms are start implementing on the other surface, okay, or foreign surface. So this process, and it is it is on the depositing on the surface, okay, or else on substrate into the substrate or on the surface. So both taking place. So this process is called as ion implementation. So these ions are either negative, okay, sorry, either positive or negative, and means this is opposite. If it is a negative, this one is positive. So positive will attract by the negative ions. Okay. So these negative ions start depositing on the positive atoms. So this is called as ion implementation. So results in an alternation of chemical or physical property layers, means it is a this process is a replacing of either CVD or PVD process, and produces a much thinner alternate layer and different concentration profile and diffusion. Okay. So when compared to the previous one, here we can produce the much thinner layer, means whatever the deposition layer is there, when compared to the PVD and CVD, here we can produce the more thin layer of filament on the substrate. So advantages of this ion implementation. Of course, this entire thing is taking place in the low temperature. So previous one PVD 500 temperature and CVD is more than 1000 degrees centigrade. But this is taking place in the low temperature and good control. So we can control the film thickness, okay, and solubility limited can be exceeded without precipitations of excess atoms. We can control the wastage of atoms here. And these are the some applications mainly used in the semiconductor devices. Sensors, we are using this type of process. Next set of process is called as a plating and related process. Plating. So, ಎಲ್ಲಾದರೂ ಕೇಳಿದ್ರಾ plating, electrolyte plating. Okay, so it's the best example. It is also type of coating purpose, coating type of coating. So coating a thin metallic layer onto the surface of substrate. So it's the putting a thin layer on the substrate. So entire process is on the surface only. We are performing entire process on surface just to modify the surface. What is the purpose of modification? Yak modification ಮಾಡಬೇಕು. What is the purpose of modification? These processes are modification process. Coating, spraying, deposition. These are all modification. What is the purpose? just to not smoothing, just to enhance the properties, just to enhance the properties like wear resistance, corrosion resistance, hardness, and lastly smoothing purpose also. Okay, so for that purpose we are going with this process. In that coating, here a plating is a one type of coating. Plating is a one type of coating. It is a coating on the metallic layer. So here we are using metallic, only metal parts, not for the non-metallic, only metal parts. Okay, and substrate as usually metallic. Here substrate as usually metallic because it produces the negative and positive ions in the electrolytes. Although the method is available in the plastics and ceramics, coats in rare cases we have to go with the plastics and ceramics. And these process, what are the process are electroplating. It's a common process is electroplating and electroforming, electrolysis plating, hot dipping. So these are the common coating methods in plating. So come to the one important process is electroplating. So electroplating process in which metal ions in an electrolyte solution. The entire thing is in the solution called electrolyte solution. The entire substrate and the other target both are immersed in the a solution. That solution is called electrolyte solution. Okay, and deposited onto the cathode work part. And here it is also called as electrochemical plating. So here anode. See here, this is a chamber. Okay, so in which this container is or a tank, plating tank or container, it is completely filled by a solution called electrolyte, solution. And here this is a positive cathode and negative, it is an anode. Is it correct? The positive one is called cathode, negative one is called anode. So this cathode is a uh, so this anode and cathode, because of electrolyte solution, it will dissolve. It will dissolve the ions, and negative ions and positive ions dissolved in the solution. That solution is called electrolyte solution. That solution dissolves the ions. And what happens when the ions dissolve and these negative ions will start depositing, positive ions start depositing on the negative ions. So here this is a workpiece. Here this is a workpiece. On this workpiece surface we have to deposit the material. Clear? And this is done with the help of electrolyte. This electrolyte will dissolve this positive particles in the solution, and these positive particles start moving towards the cathode or work part. On that work part it will start depositing. It will start depositing. But here one drawback is we cannot control the thickness. We cannot control the film thickness when compared to the CVD. In the CVD we can control the thickness, but here we cannot control the thickness. Okay, so that is the one drawback. And here direct current from the external power supply. Here we are using a power, electric power for this process. Once you supply the electric power, that will start dissolving these positive ions in the solution and start moving towards the negative. Okay, and electrolyte is an solution acid based or it is a solid based, salt or acid based. This solution may be it's an acid based or a salt based solution. So this is a one theoretical equation, Faraday's law. I think you heard this Faraday's law. Okay, that is V is equal to C by E. So on this equation it is operates. So some other common coating materials. Uh, so we are using zinc, nickel for this electrolyte materials. Zinc we are using. Okay, nickel we are using, and this is to improve the corrosion resistance, if you use nickel for a coating purpose on the substrate or any material, it is just to improve the corrosion resistance. And these type of coating is also used for decorative purpose. Decorative purpose. Okay, on steel, brass, zinc, on that we are coating. And these are the some other coating materials. Okay, copper, chromium, and some other precious materials like gold, silver. So I think you heard this gold and silver coating. So and for the jewelry purpose, okay, silver coating, gold and silver coating jewelries. So by this process they are going. And this is one example for in the kitchen appliances. Okay, so it is also coated. So this brass is coated by some other material, either zinc or chromium. It is for the decorative purpose. So this is what the process just I explained. And next important process is hot dipping. So hot dipping and this electrolysis process, they are the same process. Okay, basically they are same. But here in the hot dipping, the metal substrate or part is immersed in the molten bath. So in previous, those parts are immersed in electrolyte solution, but here the metal substrate is immersed in the molten part. This is what molten means. It is in the hot state. Is it correct? So melting point ಅಂತಂದ್ರೆ it's a high temperature. So on the molten bath, that substrate is immersed, and whatever the molten material is deposited on the substrate. So this process is called hot dipping. In the hot molten metal, the substrate is just dipped, and that the substrate before going to dip, we have to clean the surface. We have to clean the substrate surface because why you have to clean the surface? Huh? Yes, for the proper adhesion between the substrate and the filament. Okay, so ಅದೇನು filament ಮತ್ತು substrate ಇರುತ್ತಲ್ಲ ಅದು proper adhesion ಆಗುತ್ತೆ. If there is a foreign or dust particle ಇದ್ರೆ ಏನಾಗುತ್ತೆ, there is no proper adhesion. Clear? And common substrate materials are steel and iron. So steel and iron. So this process we commonly use steel and iron. Coating materials zinc, aluminum, tin, lead. So primary purpose ಯಾಕೆ ಇದು ಯೂಸ್ ಮಾಡ್ತೀವಿ ಈ process ಅಂತಂದ್ರೆ for corrosion resistance. ಈಗ iron and steel, we know that they are more reactive with the moisture. Just to avoid that one, we have to go with this hot dipping. So by the hot dipping, what happens? It will improve the corrosion resistance properly. So in ಎಲ್ಲಿ dip ಮಾಡ್ತೀವಿ ಅಂದ್ರೆ either in the zinc molten or aluminum molten state. So ಅಲ್ಲಿ just dip. Here, so hot dipping process, galvanizing. I think you heard this galvanizing sheet. I think in your workshop, you done sheet metal working. So the sheet is there. That is galvanizing sheet. Okay, that steel is coated by the either aluminum. So it is a corrosion resistant. Aluminizing and thinning. So these are the different types of coatings. So hydrophobic coating, it's a different types of coating. Okay, we just see the process. Plasma assisted CVD. So this is what a plasma assisted CVD. So here water particles are collected on the substrate surfaces. This is plasma etching. So etching means it's a cleaning process. Before going to any CVD or PVD, we have to etching the substrate. That is by with the help of plasma assisted etching. And these are the different parts which are used with the plasma etching and go for the coatings. Okay, so you just take an example of car, it's automobile. Okay, in that these so many parts are go with the coated or surface modification. And these are the some other examples plasma nitriding. Okay, so here also same thing. These are the components. You can see the connecting rods, crankshaft, sprocket. Okay, and this is what the crankshaft. Hmm. So these are all components we do with surface modification with the different processes. ಅರ್ಥ ಆಯ್ತಾ? Hmm. So surface modification, we are going with a different processes. Okay. So I will show some videos. These are the components. So vapors, these are the atoms, and this is what the substrate. From the target, the atoms are deposited on the substrate with the help of argon. So this is the PVD coated and CVD coated. They are telling difference between the PVD and CVD coated. So this is the uncoated tool. This this is what the cutting tools. Okay, tip, carbide tip, whatever working machine shop. Okay, so that is again made by this coating, surface coatings. So uncoated and after coating, so PVD and CVD coating. Just see, this is a uncoated. There is no surface is damaged. Okay, and this one is a substrate, okay, base material, and here this is damaged, and this is coated by PVD process, and it is CVD process. It's nearly same. And this after coating machining process. So chemical vapor deposition process, how it is performed. the vacuum chamber, that it's a substrate or workpiece, and these are the different gases. So like this, it will deposit it on the substrate. It's a hot dipping process. These are the casted parts of either cast iron or steel. Anode and cathode. So these anode particles are deposited on the cathode substrate. Here like this, it is deposited. You can observe the difference. Okay, with this, I'm going to